Hey, welcome back. This is now chapter 9. We begin with sequences. So it'll turn out later on that we're going to be able to approximate our trig functions, exponential functions using infinitely long polynomials. Okay, and these infinitely long polynomials can be seen as what they call sequences of partial sums. Okay, so we're kind of going to be studying a particular type of sequence, but in order to do this study we need to first work with sequences just in general. Okay, so here we go, 9.1 sequences. So first, the definition of a sequence. Okay, let's get the page correct on. So there's a lot to do today. I'm not going to lie to you. The book doesn't do the most awesome job in the universe of explaining all these little things, and now my book is frozen for some reason. Okay, so we're going to have to spend 20 minutes for me. Oh, there it goes finally. And then back here, still not there. Okay, so here we are, sequences. Mathematically, a sequence is defined as a function whose domain is a set of integers. Okay, so sequence is a function with the domain restricted to the integers. Okay, so for example, you've probably have seen sequences like 1, 3, 5, 7, dash, 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 and it doesn't necessarily look like a function, right? This is the sort of range of the function. These are the outputs. So what exactly would be the function in this case? Well, you could say f of x in this case equals 2x minus 1. But we're not going to use x. In order to indicate that we're working with the integers, we'll use a letter n, and it'll look more like this. But we're not going to write f of n. We're going to write this weirdly as a sub n, okay, equals 2n minus 1. And then to get these terms in this sequence, you're just going to plug in values, right? So if you plug in 1 for n, it'll look like this: a sub 1 equals 2 times 1 minus 1, which is 1, right? A sub 2, which is called the second term of the sequence, be 2 times 2, excuse me, minus 1, which is 4 minus 1, which is 3. And you see this guy right here is the first term, a sub 1. It's the second term, a sub 2, etc. This would be the third term, a sub 3. That formula 2n minus 1 is considered the nth term. Okay, so this is the nth term formula, nth term, and a sub n is what it's called. Okay, when we talk about the entire sequence, then the entire sequence, it's going to be given this curly bracket designation. So curly bracket, and then you put the nth term formula inside the curly bracket. Okay, and you see that here in the book. The entire sequence is denoted curly bracket a sub n. Okay. Sometimes you can begin at 0, you can begin at 1. For analysis purposes, sometimes we just don't care until eventually it's always kind of conforming to some rule. So you could chop off the first couple terms is kind of what I'm saying. You can plot these things if you want to. So for example here, 1, 2, 3 maybe, 2, 3, 4, 5. So at a sub 1, when you plug 1 into this thing, we get 1. When you plug 2 into this thing, you get 3. And you plug 3 into this thing, you get 5. So when you plot a sequence, you're just going to get a whole bunch of dots. And you'll see pictures of the sequences plotted here, like right here. They're plotting some of the points in the sequence on the right here, figure 9.1. Okay. Okay, so the first type of problems then in my math lab or WebAssign or whatever we're doing are just listing terms of a sequence. So for example, number 2, they want you to write the first 5 terms of the sequence given by this formula, this nth term formula. Okay, and it's pretty simple. You just plug in the numbers. So a sub 1 cosine of pi over 2, so that's 0. A sub 2 cosine of 2 pi over 2, which is pi, which is -1. A sub 3, which is cosine of 3 pi over 2, which again is 0. A sub 4 cosine of 4 pi over 2, which is 2 pi, which is 1. A sub 5 cosine of 5 pi over 2, which will be back to 0. Okay, so then you just type in the number 0, -1, 0, 1, 0. Okay, submit the answer, and drum roll, yay. All right, this one they're having number 3, they just want you to plot the points. Okay, so hopefully that's pretty simple. What we're going to be looking at a lot is limits, in particular limits as these sequences go to infinity, right? That's the only limit we care about. So you remember back in Calc 1, recall, you had all kinds of different limits. That is, okay, so I butchered that word there. Like the limit as x goes to 4 of 2x, of course that would just be 8. Limit as x goes to 0 from the right of maybe 1 over x, and of course that would just go to infinity. Now we only care about infinite limits. In particular, instead of x's we'll have n's, so we'll say something like the limit of 2n as n goes to infinity. And for us, that will go to infinity, of course. It'd be like 2 times 1, 2 times 2, 2 times 3, 2 times a million, 2 times a billion. Just keeps getting bigger and bigger. And then stuff like limit of 1 over n, as n goes to infinity, that will equal 0, right? It's just going to get really, really small. Some limits that you should kind of have encoded from Calc 1 and Calc 2 that I want you to be able to do quickly. Let me show you the example, one they do in the book here. Like this one, and example 3, part B. They give you, well, first let me give you the sequence. So the sequence is n all over 1 minus 2n, and they want to know the limit as n goes to infinity of that sequence. Okay, so the kind of the old-fashioned way that most people teach it in calculus classes is just to multiply the top and bottom by 1 over n. Okay, so you get n all over 1 minus 2n, so times 1 over n times 1 over n. And then you get the limit as n goes to infinity of 1 all over n minus 2. So this part will go to 0 because these type of limits go to 0 here. Anything that's the form L over infinity. And then we have -1/2 resulting. Okay, I want you to be able to do these kind of limits a lot quicker, and kind of the way you do it. So the quick method for these kind of ratios of polynomial type terms. So let's say I have the limit of 2n squared plus 3n minus 1 all over 5n to the 4th plus 2n. The trick is, and this only works, you know, if you're going to infinity, but the trick is to kind of just pick off the high degree terms, and you'll get the same exact answer. Okay, so this would be 2n squared all over 5n to the 4th. This would be the limit as n goes to infinity of 2 all over 5n squared, and of course that's L over infinity, so it's a 0. Okay, so if you've done that in the previous problem and kind of just circled those terms, these high degree terms, instead of dividing by 1 over n, you get the same answer. And matter of fact, I don't know why they don't teach it this way. It's just much quicker. N all over -2n, and then simplify that, and of course you just get a constant -1/2, and of course you get -1/2. So there's the three different versions basically. The one where the degree in the denominator is bigger than the numerator, that will always equal 0. If the degree in the denominator and numerator are the same, you just get like a fraction resulting. So if you have like 5n cubed plus 2n plus 1 all over 7n cubed minus 3n plus 5, you end up with 5/7, right? So if you just take that portion, limit as n goes to infinity of 5n cubed all over 7n cubed, you're going to get the limit as n goes to infinity of 5/7, okay, which is 5/7. The other type is when you get the numerator bigger than the denominator, and in those cases it's either going to shoot to positive infinity or negative infinity depending on the signs that you're dealing with. So let's say I have negative 5n cubed minus 2n plus 5 all over negative, or rather just positive 6n to the second power plus 3n plus 1, right? So you could just pick off the high degree parts. This will be the limit as n goes to infinity of negative 5n all over 5n cubed all over 6n squared. That will be then the limit as n goes to infinity of negative 5/6n. Okay, and that's just a line with negative slope. So as n goes to infinity, the output values are going to go to negative infinity, right? So this will be negative infinity. So it's either in those cases when the numerator is bigger than the denominator, it'll work like that. This will also apply, believe it or not, to things like the limit as n goes to infinity of 5 to the n all over 3 to the n minus 1. You could just pick off these portions, and in this case it would be the limit as n goes to infinity of 5 to the n over 3 to the n, which would be the limit as n goes to infinity of 5/3 to the n. And this thing is going to go to infinity. If you don't believe me, you can always apply your Calc 1 limit knowledge to these type of limits. Even though these are integer sequences, and technically they're not really continuous, so there's issues there, but you could apply the Calc 1 rules, or Calc 2 rules, and you could do Lptiles and stuff like that. But it would be something like the limit as n goes to infinity of e to the ln of 5/3 to the n, and then do a power rule on this, bring that right there, bring the limit into the exponent, so you'd get the limit as n goes to infinity of n times the ln of 5/3. And so long as the input of the natural log is greater than 1, greater than or equal to 1, this limit will well, if it's greater than 1, it'll go to infinity, right? If it's equal to 1, then it'll equal 0, and it'll just equal 1. If it's less than 1, then that exponent will be negative, and you'll have e to the negative infinity, which will go to 0. Okay, but in this case, this thing will go to infinity because of that thing inside here. Okay, so the moral of this story is there's a lot going on here, right? It's like not only am I now able to apply this quick method to these different types of limits, but I also note some interesting factoids. So factoid number 1, if you have the limit of some value r raised to the n as n goes to infinity, that will equal 0 if r, in particular it will be the absolute value of r is less than 1. It'll equal 1 if r is equal to 1, and then it'll equal infinity if r is greater than 1. Okay, so that limit kind of pops up every once in a while. Another limit that they just note, you probably hoping you read it, you would have noted down here when they were sort of playing around, where the heck is it? I can't even find it. When they're talking about factorials, down here, basically, if you have a limit as n goes to infinity of some exponential expression all over a factorial expression. Factorials are the fastest growing guys on the planet. So you've heard of exponential growth. Factorials grow faster than exponentials. Okay, and it just means that the bottom is going to get really big, really big, but the top isn't going to get so big, and so this is going to end up going to 0. Okay. We'll have to deal with factorials in the book, and they give you an example with regards to the squeeze theorem. In the homework, they'll have some exercises where you're just simplifying first. So like number 4, so just to the side about factorials. If you remember, what is like 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1, right? 4 factorial is 4 times 3 times 2 times 1. As a matter of fact, you can write factorials in terms of this recursive definition. So n factorial is the same as n times n minus 1 factorial. Because you could tell 5 is the same as 5 times 4 factorial. Right? It's the same idea. But in general, you'll write n factorial in this weird sort of way, n times n minus 1 times n minus 2, all the way to 3 times 2 times 1, so long as n is greater than or equal to 3. Okay, so 0 factorial, by the way, is just equal to 1. 1 factorial is equal to 1. 2 factorial is equal to 2 times 1, but that's just equal to 2. Okay, so there's that stuff. In particular, that problem in WebAssign right there, 6n minus 1 factorial all over 6n plus 1 factorial. To simplify this, we can expand it. You could use a recursive definition, which says that we have 6n minus 1 times the same thing minus 1. So the next term would be the same thing, 6n minus 1, but then minus another one. So it would end up being 6n minus 2 factorial, right? Downstairs, we have 6n plus 1 factorial. We could rewrite it with the recursive definition as times 6n plus 1 minus 1. So you just always just subtract 1 whenever you go down 1. So you'd end up with 6n factorial. We're looking for a nice cancellation. It looks like if I do one more sort of recursive definition in the denominator with 6n factorial, I'll have a nice cancellation, right? So I have 6n plus 1 times 6n times 6n minus 1 factorial. And if you look at the numerator, that's exactly what we kind of already have there. That is the same as this. So these can be removed, and you just end up with 1 all over 6n plus 1 times 6n. Okay, so we're going to be working with factorials. They're just trying to get you kind of used to that idea. Let's see if there's any other. Sure. So number 9, we have a sub n equals n minus 4 factorial all over n factorial, and they want you to find the limit of this thing. Okay, so the limit of a sub n as n goes to infinity is going to equal the limit as n goes to infinity of n minus 4 factorial, which we can rewrite, right? You can write it as n minus 4 times n minus 5 times n minus 6 all the way down to 3 times 2 times 1. So you could do the brute force definition, which is really what I did when I first started in your guys' shoes. N factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4. And I'm just looking for where I get kind of an overlap. And then n minus 5 to 3 times 2 times 1. Then you can remove the common factors. So this part and this part are the same. And you end up with the limit as n goes to infinity of 1 all over some sort of fourth degree polynomial, right? I'm not going to multiply that out. That would be insane. The denominator is going to go to infinity, right? So you have L over something going to infinity where L is just a constant, right? So those forms always go to 0, so that limit would be 0. Okay. But anyways, long story short, when it comes to limits for us, you can always apply your calculus 1 rules. Okay, so let me introduce limits on section 2 limits. Basically part A, your calc 1 rules apply. So let's see if they give us one here. Yeah, so number 10 in the homework, a sub n equals 8 to the 1 over n. We want the limit of that thing as n goes to infinity. So you could literally think of it just as x in terms of x, right? So you could think of it like it was a calc 1 problem as x goes to infinity of 8 to the 1 over x. And then you could move the limit into the exponent, so you'd have 8 to the limit as x goes to infinity of 1 over x. The limit of 1 over x is 0 as x goes to infinity, so you just get 8 to the 0, which is 1. Okay, so this is just equal to 1. Just plug 1 in there, and that's the limit. So you could do Lptiles. Technically, you're not allowed to do it with the sequence itself, but if you turn things into the x and pretend it's a function in the real numbers, then you could apply the limits, but then the limits will be equal at the end of the day. So technically, you're not supposed to write Lptiles whenever you have the letter n, which includes an integer. I didn't do Lptiles here clearly, but you know. Along with so here's one example 4 in the book. They do Lptiles. So let me just show you that real quick. So they want you to find the limit of a sub n equals n squared all over 2 to the n minus 1. So I got the limit of this thing as n goes to infinity. And either, you know, this thing is infinity over infinity, so you go limit as n goes to infinity, and see how they changed everything in the terms of x. That's what I'm talking about. Technically, you can't take the limit of a sequence and do Lptiles. You have to change it back in the x, do the limit in the real numbers, and then you could use that to make your conclusion. Okay, so just be aware, it's a technicality. I'm not going to write x every time I rewrite my limit, but it is an issue. Okay, so the numerator 2n, the derivative of 2 to the n, you may have forgotten, it's 2 to the n ln 2. Okay. It's basically, if you just think of y equals 2 to the x, rewrite it as e to the ln of 2 to the x, which is e to the x ln 2, and then take the derivative y prime will give you right back e to the x ln 2 times the derivative of the exponent, which is ln 2, and then e to the x ln 2 is just 2 to the x. So you get 2 to the x ln 2 as a derivative. Okay. All right. Anyways, this thing still is infinity over infinity, so you just do Lptiles again. And you get 2 all over 2 to the n times another ln 2, so you got ln 2 squared. And then finally, that's L over infinity form, which will just give you a 0. So at the end of the day, the limit is just going to go to 0. And one more point, whenever this thing actually goes somewhere, we say it's convergent. If it doesn't equal something, so if it goes to infinity or if it's oscillating, we'll say that the sequence is divergent. Okay. All right, so there will be here a strict definition for limits. And if you ever take like an advanced calculus, usually they start with sequences before you even do calculus, and they kind of build all of calculus from the sequences. So this limit definition becomes very important in those classes if you have the misfortune of having to take some of those. So just be aware, if you're going to become a math major, this is the kind of thing you would see a lot of. You may not like that. But anyways, the strict definition of a limit, the limit of a sequence a sub n is L, which we write LIM as n goes to infinity of a sub n equals L. If the following is true. So if for any epsilon somebody comes up with that's greater than 0, there exists some big number m, or maybe even sometimes a smaller number m, greater than 0, such that when you go out far enough in the sequence, so when the index on a sub n is big enough, in this case bigger than big M, then the sequence gets really, really super duper close to that number L. Okay, so the distance between the a sub n when n is bigger than M and L is less than whatever epsilon some person can produce, right? So we say if the limit exists, it's called convergent. Otherwise, it's divergent. Okay, so one way a sequence can diverge is if it just goes to infinity. So if you have something, let's see if we can find an exercise that goes to infinity, right? I don't think that does. That certainly doesn't. That doesn't. Well, none of them do. All right, so I guess I'm going to have to give you one. So for maybe there's one. I bet you there ain't even one in the book. I am apologizing on behalf of the book. So for example, a sub n just equals n factorial. Okay, the limit of that thing is going to go to infinity as n goes to infinity. It's just the way it is. Or sorry, infinity, not 0. Okay, so there it is. The other way, you know, there's like a couple ways. Well, there's only 2 ways, I guess, a sequence can diverge. It goes to infinity, or it has an oscillating behavior. So just note. So I can put this in here somewhere. C, part C, oscillating sequences diverge with a warning. Something can oscillate and converge. So if it's jumping back and forth about the x-axis, but then later on gets really close to the x-axis, it is converging, right? The sequence I just drew converges to 0, even though it looks like it's oscillating. So for example, if this was a sub n equals -1 to the n times 1 over n, that thing is convergent. Okay, yeah, I mean it starts at n equals 1, it's at 1, and n equals 2. So at 1, it's actually, this guy would be -1. So let's kind of cheat a little bit. N plus 1 times 1 over n, right? At 1, at a sub 1, that would be -1 to the 1 plus 1, which is 2, times 1 over 1, and -1 squared is 1, so this should be 1. A sub 2 would be -1 cubed times 1 over 2, which would be -1/2. So you see that goes below the x-axis. A sub 3 is -1 to the 4th times 1/3, which will be 1/3. So that jumps back up. So you kind of think of this as oscillating, right? But at the end of the day, it's going to get really, really close to 0. Okay, so there'll be some value m out here, such that when I get beyond that m, the a sub n's will be within some epsilon of 0, right? So epsilon and then minus epsilon. As I get past here, it's clear that those values are kind of within this epsilon strip. And they always will be. So that's the strict definition of a limit. That shows that this thing has a limit, you know. All right, so oscillating sequences will diverge, though, as long as they're not like this. This is kind of your warning. But, you know, in general, if you have an example like I just saw one in the homework, this guy right here, this a sub n, so this is number 7 in the homework. And let's make this the video quiz while we're at it. Okay, so this is video quiz set number 6, and this is the first problem in that video quiz set. Okay, so this is 9.1, and this is question 7 in WebAssign. Okay, so a sub n equals -1 to the n times n all over n plus 4. So look at the even terms and the odd terms is kind of the way I would say to approach it. And if the even terms go somewhere and the odd terms go somewhere else, then the limit automatically doesn't exist. It's called divergent. It's like you know, there's a subsequence that's going one place and another subsequence going one other place. There's no way to kind of bound that. If somebody gives you a really small epsilon that's smaller than the difference between the two places it's going, you won't be able to contain it, so to speak. Anyways, let's just investigate, right? Let's look at the even terms here. And I think you'll agree that all the even terms are going to be positive because you're basically putting even exponents on -1. And then you'll have like 2 all over 2 plus 4. A sub 4 will be -1 times 4 all over 4 plus 4, etc. A sub 2n is going to be -1 to the 2n will be positive. You know, this should have been 4. It'll be +1 times 2n all over 2n plus 4. And so the limit of these even terms, this a sub 2n thing, as n goes to infinity, what is that? It's a limit as n goes to infinity of 2n all over 2n plus 4. And I said you could just circle the high degree terms, right? This is a ratio of polynomials. So that's going to be equal to the limit as n goes to infinity of 2n all over 2n, which is just 1, right? Then look at the odd terms. Okay, so a sub 1 is going to be -1 to the first power times 1 all over 1 plus 4. A sub 3, -1 to the third power, so -1 times 3 all over 3 plus 4, etc. And then you get a sub 2n plus 1 equals -1 times 2n plus 1 all over, maybe I should make this 2n minus 1. So I'm starting with n equals 1. Okay, 2n minus 1. So this numerator would be 2n minus 1 all over 2n minus 1 plus 4, so 2n plus 3. And again, if you take the limit then of these odd guys, as n goes to infinity, you end up with a -1 times 2n minus 1. So let's just distribute the negative into the numerator. So you get -2n plus 1 all over 2n plus 3. You can circle the high degree terms, and that equals the limit as n goes to infinity. -2n over 2n is just -1, so here the limit is -1. So the deal you could take away to the grave with you is that the limit, if the limit of the even terms does not equal the limit of the odd terms, then the limit does not exist. And that's what we have in this case. Okay, so it's divergent. Okay, right. So you kind of need that process to show that this thing diverges. Yeah, you would type in divergent into the. Okay, so that was our video quiz. So, you know, proving divergence may be a little bit more difficult sometimes. Some other tools for doing limits is one other tool is the squeeze theorem. Okay, so going back to the book, yeah, here's theorem 9.3 is a squeeze theorem. So let me put that in as part D here in my notes. And you saw the squeeze theorem in Calc 1. This is just the same thing. Okay, so if you have the limit of a sub n equaling L equaling the limit of b sub n, and it's always limit goes to infinity in all of this chapter. Okay, so if that it happens and eventually a sub n is less than or equal to c sub n less than or equal to b sub n, then the limit of c sub n will equal the limit of b sub n and a sub n, right? So limit of c sub n will just equal L. So let's see if they have one like that in the homework. I'm going to have to do this on. Not really. Sorry, just thinking. I guess we'll just go with the one they got in the book. All right, so they got this guy here, example 5. Sequence is -1 to the n times 1 over n factorial. If you look at this thing, the terms are either going to be positive or negative. And so in the long run, what does that mean? It means basically -1 to the n times 1 over n factorial is always going to be stuck in between either 1 over n factorial on the top or -1 all over n factorial on the bottom. Okay, you look at the limit on the left here, the limit of -1 all over n factorial as n goes to infinity. That is just L over infinity. Even if that numerator is negative, it doesn't really affect the n behavior. It just means it's going to come in from a different direction. So for example, if you had the limit of -1 over n, and you think about that as n goes to infinity, well, what is 1 over n? What does that look like? Well, it looks like this, right? So as n goes to infinity, this thing is going to go to 0, even though it's -1 over n. When you compare that to the limit as n goes to infinity of 1 over n, you know, on the other hand, and that's just going to go to 0, but from the positive direction. Okay, so that numerator being negative doesn't affect anything, and you end up with 0. Then the limit of 1 over n factorial, I already said above that n factorial grows like bananas. It's just going to go to infinity, and of course the numerator is just some number L, so that will also equal 0. So the overall implication then is that the limit as n goes to infinity of -1 to the n times 1 over n factorial is certainly just also going to be 0 by the squeeze theorem. Okay, one thing you get for free then from the squeeze theorem is the absolute value theorem. Okay, so theorem 9.4, let me put that as part E in my notes. This is a long section, folks. A lot of stuff, a lot of good stuff. So the absolute value theorem, don't use this very much, but it does come up every once in a while, so just want to make sure it's here. Basically, if you have that the limit of the absolute value of the expression as n goes to infinity is going to equal 0, then the limit as n goes to infinity of this sequence is going to go to 0 as well. Okay. One new thing you're going to see a lot of in chapter 9 are proofs. Okay, and if you want to keep pursuing mathematics, it's all proofs later on. At least it was for me. If you go into like applied math, I don't know if that's the same thing, but for me, it was proof, 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 proof. We're not even doing math anymore. We're just doing proofs. I mean, that's how it was. So if proofs are the thing you like, you want to head more in towards math, probably like the only jobs available are like teaching and being a professor and stuff. But well, I mean, I'm not going to say that. You go work at the NSA or something like that, but you got to do FBI background checks, lie detector tests, stuff like that. May not be for everybody. So anyways, the proof, right? So what are we given, right? We're given the if part of the statement. So we suppose, you always start with a supposition of sorts, your proofs. So we suppose the limit as n goes to infinity of this sequence is equal to 0. Okay. Then we note some facts from algebra, anything that you've learned up to this point that you probably are taking for granted. So a hard part about proofs is just so much of what you know about math has been beaten into your skull. Like we all know that the planet is round and it orbits around the sun and stuff like that. Yeah, I get it. Yeah, okay. But could you prove it? Probably not. You know? So anyways, proofs are where it's at. I mean, like it or not. So we suppose, okay, so we note this factoid about absolute values, which is one of those things, right? It's okay, the absolute value of a value is in between the actual value and the negative of the value. It's kind of like what I did up here with this inequality, right? Then you could say, and you could do a squeeze theorem. So note the limit of just regular old a sub n, and oops, I started off wrong, right? So it's no, I'm good. So I need to adjust that inequality. I'm sorry. It's not quite right for what I need, because I need to be able to use the absolute value, the limit of is equal to 0. So this is also true, right? The absolute value of a sub n will always be less than or equal to a sub n and greater than or equal to 0. But a sub n itself will be greater than or equal to the negative of the absolute value and less than or equal to the absolute value. So here then we note that the negative of the absolute value of a sub n as n goes to infinity is just the negative limit, because you could factor out negatives so long as the limit exists. Limit of a sub n does exist. We know it's equal to 0, so you'd have negative 1 times 0, which is 0. And then the limit on the right-hand side of a sub n as n goes to infinity, that's just 0. That's given. We supposed that. So hence, from the squeeze theorem, then we can make our conclusion. The limit of the thing in the middle, a sub n as n goes to infinity, is equal to 0. Okay, so that's your first introduction to a proof. There will be more and more proofs. There's going to be one more proof in this section here later down the road. Looking for patterns and sequences and building sequences, definitely a lot of fun, in my opinion, compared to some of the other things we do. So section 3, I guess, pattern recognition. You can kind of harken back to your work in pre-calculus, where you had geometric sequences and arithmetic sequences. So a geometric sequence would be something like 2, 4, then 8, then 16, right? And usually the geometric sequence will be a sub n equals a sub 1 r to the n plus 1, or some variation of that, right? So in our case, maybe it's just r to the n. I sort of forget that after a while. But a sub 1 in our case was 2, and then we'll say r is equal to 2. So maybe r to the n minus 1. So a sub 2 would be a sub 1, 2 times 2 to the 2 minus 1. Yeah, that works. So 2 times 2 to the first, which is 4. Okay, so you should have formulas kind of embedded in your brain, hopefully somewhere. Honestly, when I took calculus and had the sequence stuff going on, I just guessed the formulas. So if it's easy enough, like 1, 5, 9, 13, usually you're able to guess those out, right? So it'd be like n plus 4 or something like that. Yeah, right. So, but the arithmetic sequence formula, let's just get that. It's a sub n equals, I believe it's a sub 1 plus n minus 1 times d, right? So n minus 1 times d. The d value, the difference, unlike up here, you can see there's a ratio value. The r is going to be a sub n plus 1 divided by a sub n. So in this case, it was r equals 4 over 2, which was 2, right? If you wondered how I got that. In this case, you have a d value, which is the difference between two consecutive values. So d equals a sub n plus 1 minus a sub n. In this case, it would be 5. D would equal 5 minus 1, which would be 4. Okay, so our a sub n formula this time would be 1 plus n minus 1 times 4, which would be 4n minus 4 plus 1, 4n minus 3. Starting at 1, you know, a sub 1 would be 4 minus 3 is 1. A sub 2 would be 8 minus 3 is 5, and you get it, right? So yeah, you know, they'll drag you through just kind of guessing at it, but there are these sequence formulas floating about from pre-calculus. You may want to refresh yourself on those. So anyways, let's see if they have one for us. It's nothing all that interesting. So number 13, they give us 1 all over 6 times 7, 2 all over 7 times 8, 3 all over 8 times 9. So our sequence a sub n looks like it's going to be n all over, and they tell you where n should start. So n starts 1 at 1. So yeah, n would be 1, and then below it would be n plus 5 times n plus 6. Right. So let's make sure at least a sub 3 is right. 3 all over 8 times 6, 7, 8, 9. Yeah. Okay, so that works. Taking the limit of a sub n then, because they're going to want you to find the limit of that guy. You notice in the denominator, that's a second degree. It's first degree in the numerator, so it's just going to go to 0. Okay, so it's going to be convergent. But anyways, let's see if we got it right. N plus 5 times n plus 6. Okay, and it is convergent. So they expect me to go on there and grade that. That's not going to happen. So you're not going to see me go in and grade those problems that they kind of have like a fill in the blank there. I may even have to go and take those out because I don't have time to go in there and grade them. That's silly. I don't know why they don't just grade it themselves. Anyways, from that point, you see something about monotonicity. Determine whether the results with the given nth term formula is monotonic and whether it is bounded. Okay, so at this point they're going to get into more proofy type stuff. With regards to some of these sequences, it may be impossible to determine if they're going to converge or diverge. So you kind of settle for just, I mean, you may not be able to figure out where the limit actually converges to. Okay, you may only be able to figure out if it's convergent. In our setting, that's going to be okay because we can use the terms to do approximations. We don't need to know the exact answer, we just need the first couple terms or something. Okay, so ultimately knowing what it converges to, kind of important, not really, but right, we're going to focus our efforts on just showing that something is convergent because ultimately we'll be able to use it to do an approximation. Okay, so At this point in the book, then, they're going to start talking about monotonicity and boundedness. Okay, in particular, monotonic bounded sequences are what they say convergent, right? So let me make a new section here in my notes, section 4. If a sequence is monotonic and bounded, it is convergent. Okay, and it kind of makes intuitive sense, but the actual proof of it is not intuitive. Okay, so monotonic, what I mean by monotonic is that it's strictly going up or it's strictly going down. So you have like a sequence that is going up and it's bounded above, so it never goes above this line. So you could kind of expect that it would converge to something if it's always going up, just intuitively. But like I said, that's not exactly how you're going to prove it. That's really not the proof of it. Okay, so let's get in there. So what is monotonic, first off? So let me go be a little more careful and hit my notes with this. There's two versions of monotonicity. So there's non-decreasing and non-increasing. And you have to kind of introduce, instead of just saying increasing, you have to say non-decreasing, because you could have a sequence that stays the same. Okay, and technically then it wouldn't be increasing, it's just non-decreasing. Okay, so monotonicity. First, non-increasing, which basically just means it's decreasing, but you have to deal with the sort of inequality issue, right? So a sub 1 will be greater than or equal to a sub 2, greater than or equal to a sub 3, etc. Secondly, then, there's the non-decreasing type. And that says a sub 1 will be less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to dot, dot, dot. Okay. Boundedness, then, is pretty simple. The idea is pretty simple. It basically just says that the sequence never goes above a certain number. So if you have the sequence a sub n equals 1 over n. Sorry, I butchered all that. Let's just write the sequence 1 over n. Okay, you can kind of think about the terms. It's going to be 1/2, 1, 1/2, 1/3, 1/4, 1/5. It's just getting smaller. It's going towards 0. So this thing is bounded above by a lot, pretty much any number you can think of. Like it's bounded above by 200, 150, 1, right? It's all kinds of stuff. Oh, wait a second. Okay, so it's bounded above by all this junk. It has what's called a least upper bound. So it's bounded above by 1, and that will turn out to be the least upper bound. And there's something called the completeness theorem that we kind of need in order to get away with that. It's actually an axiom, so it's not a proven thing. It's just kind of a thing that's thrown in your lap. Like okay, so with regards to boundedness, there is this issue of the completeness axiom. Which is kind of a high-powered theorem, and it basically says if you have a set of numbers, like a sequence, that is bounded above, it will have what's called a least upper bound. And then likewise, if your set of numbers is bounded below, you'll have a greatest lower bound. Okay. In general, for showing that something's bounded, it's not, you're not going to have to find these least upper bounds and greatest lower bounds. You would have to do that like an advanced calc class. You'd have to take care of that stuff. But for us, we just want to note that it's bounded above. You don't need much. You don't really need a proof in any way. But this completeness axiom will become important for actually proving, again, like I was saying, there's kind of an intuitive feel that if something is increasing and bounded above, it's convergent, but we need to prove it. And the way we'll prove it is using this completeness axiom, which is associated with boundedness, which is why I wanted to kind of introduce it right there. All right. So there's these two issues, monotonicity and boundedness. In order to show a sequence is convergent, if we don't know the limit, we need to show, one way to show that it's convergent is by showing it's monotonic and bounded. For monotonicity, you'll see in the book they give you some examples of determining whether something is monotonic, right? And they kind of do this little inequality game here. We'll have to prove things are monotonic later in chapter 9. Okay, so in order to pull that off, I want to give you some kind of methods for proving these things are monotonic. Okay, so going then up here with the monotonicity, I wanted to introduce some proof methods for that. The book shows you like an example, but I don't think it's all that good of an example. So proof methods for monotonicity. Okay, so there's two types of monotonicity that we work with, right? We either want to show that a sub n plus 1 is less than, or let's write the other way around. We want to show that a sub n is less than or equal to a sub n plus 1. So in that case, that would show that it's non-decreasing. Okay. Or you want to show that a sub n is greater than or equal to a sub n plus 1. And in other words, it's non-increasing. Okay. So the first kind of tools are algebraic tools. And that's kind of what the book is doing in that example there to the right. So for the algebraic tools, the first method is, and all you really have to do is manipulate this inequality. Okay. So what they're showing you that right there is basically you can move the a sub n plus 1 to the other side and just prove either it's greater than, okay, so you look at the difference basically. So you say a sub n plus 1 minus a sub n and then compare that to 0. Okay. If the inequality is less than or equal to, that means that you have non-increasing. Then you can also, if it's greater than or equal to, then it's non-decreasing. Right. The next kind of algebraic test is to compare the ratio to 1. So imagine that blue inequality. If you divide both sides by a sub n, you get this ratio, a sub n plus 1 all over a sub n. You want to compare that to the number 1. So if it is less than or equal to 1, basically the a sub n plus 1 term, the next term in line, is smaller. Right, so it's non-increasing. And then if it's greater than or equal to 1, it is increasing, or non-decreasing. It's a little confusing, I know. Okay. I just want to look at my notes really quick to make sure I nailed it. It's like non-increasing, non-decreasing. This stuff is just so confusing to me sometimes. So if a sub n plus 1 minus a sub n is greater than 0, it's non-decrease. And yeah, a sub n plus 1 over a sub n is greater than or equal to 1, it's non-decreasing. Okay, so this is the algebraic methods. You could also do calc methods though. So you can literally turn the given sequence into a function and then take its derivative, right? So like if you had a sub n equals 2n, you just turn that into f of x equals 2x. Then take its derivative. If f prime of x is greater than or equal to 0, it is non-decreasing. If f prime of x is less than or equal to 0, it is non-increasing. Okay, so what we want to do is kind of go through a couple examples and show that the thing is monotonic and bounded and make our conclusion. Then at the end of all that, I'll give you the proof for something being monotonic bounded being convergent. Okay. Just making sure I get this right. Okay. So let's take a look at some examples. So the first example I want to look at is maybe I can find one in the homework here. Sure. 2 plus 1 over n. A sub n equals 2 plus 1 over n. We want to show that the sequence converges, and they're kind of doing a little bit of the inequality work here. So you see they're comparing a sub n and a sub n plus 1. What I would recommend is just do a difference. So a sub n plus 1 minus a sub n, and look at that. So a sub n plus 1 is just a sub n with n plus 1 in it instead of n. So you get 2 plus 1 all over n plus 1 minus 2 plus 1 over n, right? Ultimately, we want to compare that to 0. And it's exactly what they're doing here. It's just they keep a sub n plus 1 on one side and a sub n on the other side and compare those. It's kind of the same spiel. So anyways, if you distribute the negative, the 2's will cancel. You'll have 1 over n plus 1 minus 1 over n. Find a common denominator. So on the left there, multiply top and bottom by n. On the right here, multiply top and bottom by n plus 1. Then you'll have the difference n minus n plus 1 all over the denominator of n times n plus 1. And that will just be negative 1 all over n times n plus 1. Okay. Compare that to the number 0 for n values that are positive. So for n values that are positive, this thing will be negative, right? It'll always be negative for n greater than or equal to 1. So it's always going to be a negative over a positive. A negative over a positive is negative. So that would indicate that this thing is non-increasing. Okay. So over here in the homework, what they're doing, they kind of do it a little bit different, right? 2 plus 1 over n is going to be less than 3, right? Because you're adding something that's less than 1. So this will be less than 3. That implies a sub n is bounded. Okay. We kind of did the monotonicity part first. The boundedness, I guess. So this showing monotonicity, and then part B showing boundedness. So I'll start with the fact that 1 all over n is going to be less than or equal to 1 for all n greater than or equal to 1. Okay. You can literally deduce that inequality from this inequality if you were asked to, right? Because if you just divided both sides of this inequality, presuming that n is positive, you would get 1 greater than or equal to 1 over n. And then rewriting it a bit, it's just 1 over n is less than or equal to 1. Then if you add 2 to both sides of that inequality, you get 2 plus 1 over n is less than or equal to 1 plus 2. So 2 plus 1 over n is less than or equal to 3, which is what they have in that first step there. So it's bounded. It's bounded above and below. Because, okay, so they did an absolute value. that would have been like this. And then they just added 2 on both sides. And then 2 plus absolute value of 1 over n is the same as absolute value of 2 plus 1 over n, because 2 and 1 over n are positive. And then that means it's bounded above and below, right? Because that would be expanding this inequality, less than or equal to 3, greater than or equal to negative 3. So you have that boundedness. Okay, so it is bounded above and below. So hence bounded. Okay, so there's the boundedness issue taken care of. The next part, they're comparing these, right? So what did we show? We showed basically, a long story short, that a sub n plus 1 minus a sub n is less than 0. In other words, a sub n plus 1 is less than a sub n. Okay, so they want it the other way around. Basically, they want a sub n is greater than a sub n plus 1. So a sub n is, they only give us the greater than or equal to, so we use that, greater than that. So as I said already, this is monotonic, and in particular non-increasing. Okay, so it's going to be going up from 2 and kind of get really, really close to 3. So it's starting at 2 and then getting close to 3. So it'll be this version here. Finding its limit, that'll just be 2. Okay. Or it's actually, yeah, the limit is 2. But if you plot the first 10 terms, well, it's going down from 3. So it's going to be this one, sorry. And then it's getting smaller and getting closer to 2. Okay, so let's submit the answer on that. Okay, so whoops. It's less than or equal to 3. That must be it. Sorry. Yeah. All right. Great. They got any other of these? Sure. There's this one here. Number 14, a sub n equals n e to the negative n over 5. They want to know if it's monotonic and or bounded. The boundedness issue, e to the negative n over 5, once we get past so if I were to graph that thing out at 0, we don't really care, but at 0 it is 1, right? So it's going to be here, and then it's just going to drop down from there. So it's going to be, it's an exponential decay, so it's going to go like this. So eventually it is, yeah, it's bounded above. If you start at 1, this thing will be bounded above by 1. Is it bounded below? Well, n is positive. N is greater than 0. E to the negative n over 5 is also greater than 0. Thus, the product will be greater than 0. Hence, n times e to the negative n over 5 will be a positive times a positive, which will be a positive. In other words, greater than 0. So it is bounded below by 0. Okay. Then is it monotonic? So this is where I would use the derivative as opposed to using some sort of algebraic monotonicity test. Okay. So taking the derivative f prime of x, that's going to be, take the derivative x, and then you have e to the negative x over 5 times negative 1/5. And then plus, leave x alone and take the derivative e to the negative x. I did that wrong. Okay, sorry. So it'd be e to the negative x over 5, just times the derivative of x, which would be 1, and then plus x e to the negative x over 5 times the derivative of negative x over 5, which is negative 1/5. Okay. Sort of set that equal to 0 to get the critical points. E to the negative x over 5 times 1 minus x over 5. So our critical point This thing is always positive, so it'll never equal 0, but the other guy will. So solve that for x. So x is equal to 5. So only care from 1 to infinity. At 5, what's happening, this derivative is going from, let's see, how's it behaving? And so if it was like 2, this would be positive, and then this would be negative. So it's non-increasing. So it is monotonic, and monotonic and bounded. Monotonic and bounded. Where is it? There we go. Okay. Okay. It isn't bounded. I'm sorry. I guess it's in the beginning it's not monotonic, but eventually it is. So maybe they just want not monotonic, because in the beginning it is going up and then it goes down. So I guess that's what they want. But ultimately it is monotonic and bounded past n equals 5. So you would say it eventually converges, even though the book is kind of beating you up over it. Okay. The other kind of monotonicity test I just want to show you really quick is kind of the ratio. It's kind of a ratio type test. It's the this test right here. Okay, so for example, I'll just give you an example. A sub n equals 2/3 to the n, right? This guy is bounded. It's bounded above by 1. It's bounded below by 0, so it definitely is bounded. Secondly, then, is it monotonic? So in this case, I'm going to look at the ratio of a sub n plus 1 all over a sub n and compare that to the number 1. Okay, so I'd have 2/3 to the n plus 1 all over 2/3 to the n, and that'll equal to just 2/3, and clearly that is less than 1. So it's decreasing, in other words, non-increasing, and eventually, you know, for n, well, n greater than 1, basically, greater than or equal to 1. So definitely convergent. Okay. Okay, so hopefully that helps you with these monotonicity tests. There's only 2 in the homework, though, so it's really not going to affect you. Anyways, ultimately we need to go to then your proof for this monotonic bounded, and we need the completeness theorem. Okay, so basically, again, the completeness theorem says that if you have a set of numbers that are bounded, then there's going to be this thing, a least upper bound. We're also going to need to harken back to the strict definition of a limit. So let me just remind you again of the strict definition of a limit. Okay, so this will be part, I guess, C, the proof. And so we have a reminder of the strict definition of a limit, which says that the limit as n goes to infinity of a sub n will equal L if for any epsilon greater than 0 there exists an big M greater than 0 such that if n is greater than this big M, then the distance between the nth term and L is less than epsilon. Okay, so we want to show that that's true if we have the supposition that the thing is bounded and monotonic. Okay, so the proof. So again, we suppose a sub n is bounded and monotonic. Let's suppose that it is non-decreasing. Okay, so in that case, because it's bounded, there must be an upper bound. Okay, called, I guess we'll call it big N, or maybe even big, let's call it big, because I'm going to be using big N, but then I have a big M in this definition, so it's going to be a little confusing. Called big, we'll call it big P, all right? I apologize if that blows your mind. Okay. So the way the sequence will behave, because it's non-decreasing, it'll be like a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3. That's the word so. Less than or equal to a sub 4, etc. Less than or equal to a sub some n, less than or equal to etc. And then all of that is going to be less than or equal to this big P, this upper bound. Okay. Then from the completeness axiom, we could do even better than big P, right? From the completeness axiom, there must exist a least upper bound L such that the sort of the same thing holds true but with an L that is less than or equal to this P. Okay, so you have a sub 1 less than or equal to a sub 2 less than or equal to a sub 3 less than or equal to dot 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 less than or equal to a sub n is less than or equal to dot 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 less than or equal to L. The difference between L and P is that anything less than L is going to be in this sequence. Okay, it's the least upper bound. So if there was something lower than L that was not in the sequence, it would not be an upper bound. I mean, L would not be an upper bound in that case. Okay, so again, let me say that. If there's something less than L that is not in the sequence, that thing would be the upper bound, right? So there can't be anything less than L that is not a member of that sequence, weirdly enough. Okay, or maybe not even that. It's not, because there wouldn't be a continuity issue. If you have something less than L, there'll be a member of that sequence which is greater than or equal to that thing. Okay, so what I'm saying is, okay, so just take a small number like epsilon. Take a epsilon greater than 0, right? We note then, well, clearly L minus epsilon is less than L. And then in between there has to be numbers of the sequence that are bigger than or equal to L minus epsilon, right? So because L is the least upper bound, it must be the case that at least one term of the sequence a sub n exists such that, and let's call it a sub big N, this thing is bigger than this a sub big N, because if that was not true, then L minus epsilon would be the least upper bound. Okay. For if not, then L minus epsilon would be the least upper bound. But we can't have that because we already said that L was the least upper bound. Okay. So, so from that point, you could say, thus, for any little n greater than or equal to this big N, those terms of the sequence will be, because it's non-decreasing, those terms will all be bigger than this a sub n, a sub big N, which is bigger than L minus epsilon. And that will be true for any value afterwards. So for all n greater than or equal to n. I think I kind of already said that. Okay. Thus we could say And here's the punchline. For any epsilon greater than 0, there exists a big N such that if little n is bigger than this big N, then the distance between a sub n and L will be less than epsilon, which is the definition of a limit, a convergent limit, right? We just kind of created the definition. So it's a real clever proof. It's kind of weird, but there it is. So hence, monotonicity plus boundedness equals convergence, and that's it. Okay, a lot of work there. I just want to look at this number 16 because it actually looks kind of weird, and I'm probably going to go back there and delete these ones where you have to type in your own answers so it's not scoring against you. Anyways, number 16 is kind of weird. Compute the first 6 terms. I'll presume you could do that. If the sequence converges, fine. Oh, so you should be able to do that, but I'll do it anyways. So the limit is n, the nth root of n. You would just figure out the limit of n to the 1 over n, and that's like an infinity to 0 form, so you kind of already know how to do that. I thought maybe it was something else, something weirder. Okay, I think you should be able to handle everything else then. As usual, thank you for watching. Sorry the video is so long, but a lot of these sections are like that. So dig in, and thank you for watching, and we'll see you next time.